Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So sound check. So can you guys hear me? Someone please respond. Okay, very good. So let's continue. Okay, so before we start, just a reminder. So actually, this is a test one. So our test one is already postponed to 25th of November. So we will do it at class time. The test will be 1 hour, and the coverage will be from week 1 until week 4. Okay, so which is a Z transform, so which will be covered this week. So this is 1 hour. So we will have another hour on Thursday. So then we'll finish the part where it will, which will be covered in test one. Okay, so all right, and after this week 6, so means that next week we still have another topic on Z transform, but will not be covered in test one. So after the test one, we will start the assignment later. Okay, so now the topic is, this is a new topic, so we call it a Z transform in a continuous system and a continuous signal. So actually the topic is a Laplace transform. Okay, you have actually learned Laplace transform, I think at least 2 times. One is one in maths courses, one math course, and then in signal system. So you already also did that Laplace transform. Okay, so, and in the continuous domain, so that Z is actually S. Okay, so now we change it into Z. So in terms of S, now it is a Z. So we call it a Z transform. So why do we need this Z transform? Why it is important? So you have learned that. You have, what do you think? So because you already learned Laplace transform. So what is a Laplace transform? So why do you need that? And it's not easy. Sometimes it's not easy to do that, Laplace transform. So why do you learn that? Anyone remember? Or maybe you can just respond, I don't remember a thing from that one. So did you still remember the name, Laplace transform? Anyone still remember that? Laplace transform? No one? No one remember? What is a Laplace transform? So now we have a Laplace. Everybody already sleeping. Okay, so time to wake up. So this is Z transform. It is actually a version of a Laplace transform for discrete time. All right, so we have I listed three purpose why we use the Z transform. Okay, number one is to convert between a difference equation and impulse response. So we have done this for FIR system last time, but we didn't cover on how to convert between difference equation and impulse response for IIR, for infinite impulse response system. So this is where this is the time we need to do that, because we need to use Z transform. Second one is to evaluate the stability and causality again. So we already know 2 methods on how to evaluate stability and causality. The first one is we are looking at the difference equation. We are looking at the difference equation, the relationship between input and output. So where we see input, output, and the process. So we can evaluate the stability and causality from there. And we just covered the second method in our first session, evaluating stability and causality based on impulse response. Stability means the sum of all values in the impulse response supposed to be less than infinity or not equal to infinity. And causality, when checking on impulse response, so it should be all the values, the Hn, must be 0 for n less than 0. Okay, so we have done that. And a Z transform, so we can use a Z transform for another option on how to check stability and causality. So actually we have three methods. Okay, in this course we cover three methods on checking stability and causality. Okay, so we will look on that one later. And number three is to design an LTI system based on the poles and zeros of the Z domain. Okay, so this is even later. This is week 12, 13, 14. Right? Stability and causality, this is this week. So, and then this one, this is not this week. Number one, this is not this week. I think this is another 2 weeks. Maybe next week or maybe another 2 weeks. Right? So, and when doing a Z transform, so this is where I ask you to watch this a few videos. Okay, so what is it? This is actually on a geometric sequence, and this is the finite geometric series formula, right? So we have a geometric sequence. This is geometric series, and then there is a sum of infinite. So this is a finite, this is infinite. So the same thing, what we have here. So we have FIR, finite impulse transform, and then we have infinite impulse transform. So that's why everything is actually is not, all these maths doesn't start with DSP knowledge. So actually DSP is just using the maths. So actually DSP just using the maths. And why we are using this geometric sequence? Because everything is discrete. And when it is a discrete time, all values are actually in sequence. Okay, so that's, we already know that. We already discussed that many times. Okay, so, and you have seen the formula, so hopefully everybody already watched this video. So you already know what is what happened if you do a finite geometric series formula. When you do the sum of infinite geometric series, so there is a term, so we call it a convergence and divergence. So we will use this. We will use this for DSP, so to do something, to do some analysis. Okay, so that's why it's very important to watch these videos, because this is actually a very simple maths, and we're going to use it for DSP. So if you doesn't watch this, so maybe it will be a little bit difficult on understanding our topic and now. Okay, hopefully everybody already watched it. Okay, so let's read this one for FIR system. So this is what we have done last week. The conversion is straightforward based on the coefficient B. Okay, let's recap a bit on that one. So if we can have, let's say, example of LTI system. Or actually, I have a better slide for that one. So we have seen this. So this is one example of difference equation. So how do we know that? How do you know this is linear and time invariant? Because when we look at the operation, so we only have weight multiplication, this thing, and then summation, and then delay. So that's all. So this is confirmed LTI system. And those values, those green and that orange values, so those are what we call a coefficient. Those are what we call coefficient. And those values, which is multiplied to the output sequence, so we call it coefficient A. And those values, which is multiplied to the input sequence, so we call it coefficient B. Okay, so and this is where, when we do this for FIR system, conversion is very straightforward because we are looking only at coefficient B, just a single coefficient B. All right, so when we do that, so Hn is just for FIR system, Hn is actually equals to B. So whatever this value, this is a 232, so that is actually Hn for FIR. But for IIR, so we need Z transform. So this is what we need to do here. Okay, so for IR system, the Z transform properties will ease the conversion. Note, in math, generally, a transform can be used to manipulate values on a plane to a more desirable form. So this is why we need a transform. So what is actually a transform? Okay, we will talk a bit on some conceptual, this maths theorem. So Actually, Z transform, Fourier transform, Fourier series is not DSP, it's not signal and system materials. So actually it's maths. Actually it's maths. So maths person design the things when it said the transform. So actually we are transforming certain values in a domain, okay, into another domain. So why do we do this? So why do we do this? So why do we do the transform? So because at our case, what we have is actually time domain. We call it time domain, and then we're going to convert it into Z domain. So we call it Z domain. Okay, so all those values that we have, let's say inputs signal, there's a sequence of values. Okay, and then we have a system. So we have input signal, and then we have impulse response. And to get Yn, so we need to do convolution. Sometimes doing convolution is a bit hassle. Okay, so we can have maybe some options after we convert everything into a new domain. Then the maths change. So the maths change. So normally, so this is what we call a desirable form. So the maths becomes easier. The maths becomes maybe a simpler. The analysis becomes easier also. And we can see something which is not shown in the time domain. So that's why we do transform. So that's why actually a transform is not unique for signal processing. So it is actually done to many areas. So, but we have our purpose on what when we do a transform. Okay, so we will involve two types of transform, which is a Z transform and Fourier transform. Even Fourier transform is not signal processing; it is actually maths. We use it. Okay, and actually Z transform and Fourier transform is in one family. So it's not other type of transform. And to say that, Fourier transform is actually just a subset of Z transform. So means Fourier transform is just a small part of a Z transform. So that's why we start with the Z transform first. Before we go a little bit deeper on that transform, which is what we call a Fourier transform. So, but what is the purpose? So one of the purpose is so that we can get a more desirable form of the equation, so that we can manipulate the equation easier and better. We can design it easier. We can analyze when we do analysis on a time domain, so that we can get a better analysis in the other domain. Okay, so that's the purpose. So transform, right? And actually, you already learned about a few. The one that you guys already learned is in maths, is what we call a geometric transform. So you done that. So you have a plane, and then you convert it into something. There's a translation, rotation, this kind of thing. Those are transforms. So this is another transform. Okay, so I'm going to skip this one. So what is a Z transform? So transform a discrete time signal from time domain. We call it time domain. Why it is a time domain? Because the x-axis is time. So for discrete time signal, the time is n. So we use the notation is n. Okay, we don't use t. So t is for continuous time, right? To Z plane. So this is what we call a Z plane or Z domain. So you can say that a plane, a domain, same thing. Okay, from time to Z. And this is actually a polynomial. Okay, skip that, ignore that. So Z plane is a complex plane as shown below. So now you can imagine that. So in time domain, you have only one axis, which is the time axis. So of course you have another one, which is the y-axis. Okay, so this is a y-axis. Y-axis normally, what is it? So normally it is an amplitude. And it depends on what are the signal that you are capturing. So if it is audio, you are capturing using a microphone. So it is a sound pressure. Okay, if it is a temperature, so it's supposed to be in temperature, either Celsius or maybe Fahrenheit, those kind of thing. Okay, so that y-axis it depends on what are the things that you are measuring or recording. But the x-axis is time, which is n. So now when we convert this time domain into a Z domain, so this a single axis now becomes 2, because this is actually what we call a complex plane. So what you get is actually this is n. We're going to transform it. So if this is what we call amplitude, this is amplitude. This is a Z amplitude. So this is a time amplitude. So now if we call this is a horizontal, let's say this is a horizontal plane, a horizontal axis. So now we have two horizontal axes. One is real, another one is imaginary. So you are converting or you are transforming this real value into a complex value. Okay, sound complex, because this is a complex plane. So don't worry, because the maths is supposed to be not that complex. Okay, so this is what you're going to observe in this Z domain after the transform. So what can we have? Okay, so we can check stability, causality, and then we can do some maths and manipulation, because the maths is normally actually is not normally, it is easier. It is easier. Okay, rather than solving the system in time domain. So it is actually easier solving the system in Z domain. Right, so that's why we are going to design this system later using this Z domain. And this is a formula. It's very familiar, because if you already watch those videos on geometric sequence and series, so this is actually quite familiar. This is actually geometric series, right? So what is a series? What is a sequence? Sequence is a value in sequence. So you have index. So then what is a sequence? Series is you have a sequence, you do summation to all those values, but of course with some formula. So then what is a series? Okay, so this is a series because you can see the summation here. So this is a series. And you can see that, so there's a h n z to the power of minus n. And if you already watched the video, so there's a one term, we call it a common ratio. Okay, so we're going to understand everything based on the common ratio. Okay, that's the formula. Let's do something. Okay, what is this? So this is a region on the Z plane where the magnitude of Hz is not infinity. And yes, so we already have, we also have that when we do sum of infinite geometric series. So it means that you have a sequence. You have a sequence with infinite length. Okay, so with infinite length, and then you do the sum using a geometric series. So there is some situation that's the value can be equals to infinity. So this is what we call it doesn't converge. It doesn't converge. So if it is converged, the value of the sum is supposed to be less than infinity. Okay, in DSP, so we call it a region of convergence. So any region, any values, any Hz. Okay, looking back into our this plane. So what is this? So this is a Z domain. So we have on the horizontal axis, the real and imaginary axis. And then this is the Z amplitude. So I'm going to change that now. So this is actually the Hz. So what is the formula again? We are trying to get Hz. So what is this Hz? It is that vertical axis. This is the vertical axis. Okay. So Hz, that one is a Hz. So we're going to, we need to find out, so which region, which real and imaginary value that give Hz not equals to infinity, and which Hz, the imaginary and real value, that will result Hz equals to infinity. Okay, we need to know that first. So there's a use for that. There's a use for that. But we need to find that one. Because it is a sum, it is a series of infinite sequence. We can have that. For FIR, it is finite. For IIR, so we will have that situation. Okay, let's look for one example. So this is an example because we are going to look at on an example which it has both infinity and non-infinity, Hz. So it is good to start an example with IIR system. So how do we know this is IIR system? So we need to check the length of this system. So this is Hn. Hn is a system. If it is Xn, then it is a signal. Okay, so we need to check is this what is the length? What is the length? So if we plot this, let's say if we have H0, so you will see this is alpha to the power of 0, U0. So what is a UN? UN is a step signal. And this one becomes 1. Okay, whatever the value of alpha is, to the power of 0 becomes 1, and U0 is 1. So what is a step signal? So this is step signal. 0, 1, 2, everything is 1 until infinity. Okay, so this is UN. And what is alpha n? What is alpha n? So alpha n is at 0, alpha to the power of 0 is 1. You will start with 1. Okay, and then it depends on what is the alpha is. So for example, let's say alpha equals to 0.1. So what will be next? 0.1 to the power of 1 is 0.1. 0.1 to the power of 2, okay, so that will be a 0.01. And you can do that until infinity. So this value is actually very close to a 0. Okay, so it becomes smaller, 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 and smaller. And at -1, so this one becomes, because this is a 0.1 to the power of -1, you'll get 10. The next will be 100. The next will be 1000. Okay, until minus infinity, you will get something infinity. So that is actually alpha n. But because this signal is alpha n multiplied to un, so you need to multiply this one to this one. All right, so what happened? So whatever the n value, which is negative, everything is 0. So multiply to 0. So what you have is actually what's left. It will start at 0. Okay, so for n, negative n, everything will become 0 because you already multiply with 0 because of the un. Because of the un. Okay, so clearly, what is the length? The length is infinity because you have values from 0 up to infinity. So this is IIR. Okay, infinite impulse response. Why infinite impulse response? Because this is impulse response. So we just need to know what is the length. So the length is infinite, so we call it infinite impulse response. Okay, so this is one example. And of course, you can do that. Let's say alpha to the power of n. This is alpha equals to 0.1. So you can do that also if, let's say, alpha equals to 2. Then you can sketch, right? So you can sketch. So, but the length is still infinity. The length is still infinity. A different plot if alpha equals to 2, but the length is still infinity. Okay, so now we need to do a Hz. Because why do we need to do a Hz? Because it can simplify our calculation. We can do some analysis on it, right? So, but those are the application of it. So, but now we just need to know how to convert this impulse response into a Z domain. Okay, so this is the formula. The formula is just a summation of our Hn. Our Hn is alpha n un. And you just multiply with Z to the power of minus n. Okay, so you just add up this thing. Multiply with Z to the power of minus n. Actually, generally, any transform, it should have what we call a transformation basis. So this is actually the transformation basis. So for Fourier transform, we will have another transformation basis. Later we're going to look at that one. Okay, but of course, you doesn't need to remember that the name is a transformation basis. So that's quite a little bit advanced if you want to go for more detail on it. So just multiply with that one. We have a range here. So the range is minus infinity to infinity generally. But because we know that un is from 0 up to infinity, so then we can just remove the un, remove this un, and then replace the range, which is from 0 up to infinity. Multiply with z to the power of minus n, and then you group that one, then you get something like this. So this is the alpha z to the power of minus 1. And what is this? From the videos, so this is what we call a common ratio. So that's our first objective. So we need to find out what is a common ratio. So because after we get this common ratio, so we can do the next step. And we have seen this equation from the videos. Okay, so we already know how this equation is actually derived. So there's one video how this equation is derived. Yeah, and actually it is a very simple on how it is derived. Okay, so then we plug in all the values. So this is what we get. So this is the common ratio again. So this is the common ratio. So the common ratio, you need to put a power of 0 because we start at 0. And then the common ratio again, put it on the power of whatever the n value here, plus 1. Okay. So do that. So what we get here is, and this is also the same thing. So if you watch this video, geometric series convergence and divergence, or sum of infinite geometric series. So this is what is actually being discussed. To make sure Hz converge, which is not equals to infinity, that common ratio, which is the Ez to the power of minus 1 in our case here, must be less than 1. Must be less than 1. So this one must be less than 1. So what happened if it is if Ez to the power of minus 1 is greater than 1? So you will get this term equals to infinity. Okay, let's say this is 2. Let's say Az to the power of minus 1 is equals to 2. So Az minus 1, let's say this is equals to 2, then you will have these terms becomes 2 to the power of infinity plus 1, which is infinity. So okay, so we need this Ez, the common ratio, to be less than 1 in this case. In this case, Ez to the power of minus 1 is supposed to be less than 1, so that Hz will converge. So so this is we already know that. So this is why let's see, maybe I missed something here. So when Ez to the power of minus 1 is actually supposed to be less than 0. less than 1, then this is actually alpha z less than 1, and this is actually z greater than alpha. Okay, so I missed that one. So this is what we get. So to make sure our hz, so hz is actually equals to 1 over 1 minus alpha z to the power of minus 1. So this is what we get from this equation. This one. Okay, why this is 1? Because this is to the power of 0. And then you get az to the power of minus 1. This is, if it is less than 1, so this one becomes 0. And then 1 minus alpha z minus 1. Okay, so, and we will get this thing if the z is greater than alpha. So this z, if that z is greater than alpha. If the z is less than or equals to alpha, so we will get infinity. So this is hz. So this is a complete equation of hz. So we need to know, because if it is an infinite summation, which is the infinite impulse response, so we should find out this thing, because we need to know what is the z value that give hz a value, or z value which give the hz equals to infinity. Okay, because we need to know this. So the range where the range where hz not equals to infinity is called a region of convergence. Okay, this one. This is what we call ROC, region of convergence. And because let's read the last sentence. Because z is a complex value. Okay, so z is actually a complex value. So if you remember, I sketched this one. So this is a z domain. So this is a z domain. So it consists of real and imaginary. Okay. So this is actually a z, the real plus imaginary. So that one is actually z. So that's why we put it as a h to the function of z. Okay, what is that z? Z is actually real plus imaginary. So that one is a z. So, and of course, we can also write this as a h real plus imaginary. And we don't do that normally because we're going to put it as we simplify it as a z. Okay, so we don't write h real plus imaginary. So, but we know that we need to find h for if this is let's say a point here. So what is the real value? What is the imaginary value? So we should know, and then find what is the value on hz. Okay, so this is the one that we are computing. Either it is infinity or not infinity. Okay, all right. And because this is a complex value, again, complex value, most of this, what I'm actually explaining is actually, most of it is actually maths. Okay, most of it is maths. Because z is a complex value, it can also be written in polar form. Okay, again, revision. This is a revision on maths. So we call it a polar form. So z equals to Rej theta. When you have a real, imaginary, you have a point there. So either you can have, what is the value here? Let's say this is alpha. Let's say this is beta. So alpha is a real value. So what is the real value? And then beta is the imaginary value. But we can also represent this point using a polar form. So which is, we should know what is the radius. Okay, the radius and the angle. The angle of this line from 0 degree. So this is where we can put it as a z equals to, in polar form, what is the radius, and then exponent to the power of this imaginary of that theta, that angle. Okay, maths. So this is maths. So thus, the range of the ROC is actually determined by the radius r. So actually, it is determined by the radius r. So we have now this one, which is the r. Because z, we can look at this. We have that absolute value notation. What is this? So this is actually the magnitude. The magnitude is r. So how do you get r? Real squared plus imaginary squared, square root. Okay, so everything becomes positive value. So this is what we get. So that's why z is actually the radius. That one is a z. That z absolute value. Right? ROC is based on that. See, we have all those things. We have the absolute value here. We have the absolute value. So we are actually looking at the radius. So this is when we want to sketch, and this is actually the top view of the Z domain. So because previously I sketch it this way. So this is a real, imaginary, and then this is the HZ. And what is this? So this is actually, if we are looking at this, so this is actually top view. Okay, we are looking at the top view. So we are sketching on the top view. So when you look from top, so what you see is this imaginary and real. Okay, this is the imaginary, this is the real. And why we do this? Because we just need to know which area is actually giving us infinity value and which area giving us values which is not infinity. What is the value if it is not infinity? Not important. It is not important to know. What is the value if it is not infinity? So what is important is either it is infinity or not infinity. Okay, so that we know the region. So we know the region. So because the ROC previously from this example, the ROC is actually Z greater than alpha. So actually we have alpha here. Alpha. So you can draw a circle. So that is the alpha. So whatever the value in that region, so it is actually converge, which is not equal to infinity. And if you compute the values within this region, so the value will be infinity. The value will be infinity. Okay. Not greater than alpha. I think that one is okay. Greater than alpha. Okay. Okay, so that's how we transform. We transform a time domain, a signal or system, where a system is represented by impulse response, into a Z domain. So what we should have is this kind of equation. So we should get this kind of equation plus ROC. So we need to have both. Then it is complete. And actually, this one later, we can simplify this. Because we already know that other than Z greater than alpha, everything is supposed to be infinity. So actually, we can just write it as h Z equals to 1 over 1 minus alpha Z to the power of minus 1, which is Z greater than alpha. So actually, this is enough. This is enough to write it. So we doesn't need to write this one. Okay, because this slide is just it is an introduction on how to convert the time domain into the Z domain. So actually, there is this line. But to simplify this equation, we can just write it this way. Okay, without the second line, because we already know that this is actually infinity. Okay, any questions? So that's what I mean. If you already watch the videos, it will be easier to understand. Okay, it will be easier to understand that one. Any questions so far on how to convert that? So okay, next we have another 10 minutes. So this is a impulse response test last time. So in previous chapter, it has been shown that how the LTI system is evaluated on its stability and causality based on impulse response. So this is what we have seen in our first session today. Okay. So causality, Hn equals to 0 for n less than 0. Hn, the summation of Hn is less than infinity. That one is to check stability of that system. So now we're going to check this causality and stability based on a Z domain. Okay, so this is going to be the third method on how to test this stability and causality. So why stability and causality is very important to check, because it will determine whether your system is practical or not practical. If the system is not stable, you cannot implement it, definitely. If it is causal, okay. If it is not causal, you cannot implement it on an online system, on live system. You cannot implement it. If it is offline system, actually you can do it. Non-causal system is only for offline system. But if you have an online system, your data is coming in live, so you cannot do the causal, the non-causal system. If you have a data, you already record it and then save it, and then you process it later. So that one, it is possible actually to use the non-causal system. Okay, so that's why it's very important to check stability and causality. So now this is the third method. We are using this Z domain, Z plane, on how to check causality. Causality of the LTI system will determine the shape of the ROC. For causal system where Hn equals to 0 for n less than 0, this is by checking the impulse response. ROC is called a right-handed. Okay, we call it right-handed. And this is for anti-causal system. So we call it a left-handed. Okay, just we are looking at the term first. One is a right-handed, another one is left-handed, and then this is for non-causal system. So actually we have another option. This one, so we can have a ROC, either this one. Okay, center, everything is infinity, and then this outer ring. So you will have your values, which is not equals to infinity. Okay, this one infinity. And then you have another shape, which is inside that circle, everything is not infinity. But outside that circle, those will give you an infinity value. Okay, those lined or shaded is actually the one which is not infinity. And we have another shape. When you do this system, you will find either the first one, this is the second one, or this one, the third one. It is a ring shape. So it will be a ring shape. So there will be this region, and then at center there will be some region which is infinity, and then this outer ring. So it will be infinity also. Okay, so whatever you do, so you will get only these three types of ROC. So it's not possible to get other than these three. Okay, so which one is causal? So this is the only shape which is actually will give you a causal system. So this is a causal system, not this one and not this one. This is not causal, this is not causal. So only if you get this shape of ROC, so it is a causal system. Okay, so not that difficult, because we only have three shapes. So whatever you do when you do HZ, you will get either one of these. Okay, so we will have time to look at one example. So let's say Hn is equal to an un. So this is actually from our previous example. So this is a causal system. So this is wrong. This is not a signal because this is impulse response. Okay, so slash that. So this one supposed to be system. Okay, there's an error in the notes. So then we do that H zag, do the summation, and then multiply with zag to the power of minus n. So this is the formula for H zag. And then you will get this one. This is a common ratio. And then we check the common ratio. So that's this common ratio, this one. So we need to make sure that this doesn't give us infinity. So to do that, so you need to have E zag to the power of minus 1 less than 1. So we have done this. Okay, so thus, so H zag is actually equals to 1 over 1 minus alpha zag to the power of minus 1, where the ROC is a zag, absolute value of zag, which is greater than alpha. Okay, I write it as an A here. So because this is greater than, so this is what we call a right-sided ROC. Okay, that symbol, greater than. So if you get greater than, so this is causal. This is causal. Only if you have greater than. And this is another example. So let's say Hn equals to minus alpha to the power of n u minus n minus 1. There's a lot of things here. Okay, so this is u minus n minus 1. So this is actually step signal. Has been deleted and folded. Okay, deleted and folded. So this is actually non-causal, or we call it very, very special. This is actually anti-causal. Anti-causal is a non-causal, special case of a non-causal. So this is an anti-causal system. So if this is a step signal, so this is the u minus n minus 1. So we flip it. We flip and then delay by 1. So it starts from minus 1 until minus infinity. Right? Still IIR, infinite impulse response, because we have infinity number of samples. So what are the samples? From minus infinity up to minus 1. So we have those samples. And of course, clearly, this is a Hn. The Hn is not 0 at n less than 0, because this is supposed to be 0 if it is, if you want it to be a causal. But this is not 0. We have a value of 1. So we know that from Hn, this is actually non-causal, not causal. But let's check it on the zag domain. So how to prove that in zag domain it is also non-causal. Then we put it the formula for zag. So this is actually from minus infinity, because we have a from minus infinity here until minus 1. Till minus 1. So then this is the alpha minus alpha, because we have a minus here, minus alpha to the power of n, zag to the power of minus n, and then you group it so that you get your common ratio. That minus, you bring it out over here. So this is your common ratio. And if you look at this common ratio, actually this is the same. So you will have the same common ratio. So you have the same common ratio. It's just that now this is to the power of minus infinity, and this is to the power of 0. Previously, this is to the power of 0, and this is to the power of infinity plus 1. Okay, now it is different, swap. It almost like swapping it, right? So because we have this e zag to the power of minus 1 to the power of minus infinity, so this is where to make it converge. So you need to make sure that this common ratio is supposed to be greater than 1. You need to be make it to be greater than 1. So you have e zag minus 1. This is supposed to be greater than 1. And then you will have this a over zag supposed to be greater than 1. And then that zag supposed to be less than a. Now you'll have less than instead of greater than. So this is finally you get h zag equals to 1 over 1 minus alpha zag to the power of minus 1, which is exactly the same with our previous example. So what is the difference? The ROC. So the ROC now is a zag less than alpha. If you see this, or if you get this one less than, then this is actually non-causal, right? Causal system, the ROC is supposed to be greater than only. So this is less than. And this is the shape of the ROC. So this is the A. So less than A, radius less than A, so you should get a converged value, which is value which is not equal to infinity. The rest, this area, this wide area, the value of each z is equals to infinity. Okay, and then if you go for another example, this one, do that. Okay, as an exercise, so you will get something like this. The ROC z is greater than 0.5 and z less than 2. So which is you have two things. One is a z less than, another one is a z greater than. Okay, so you see this less than. So whenever you see a less than, this one, so it will be non-causal. Okay, so this is the third shape. So ROC will have only you will have only 3 shapes. So only the first shape, which is the right-sided, will give you causal system. Okay, so I will stop there. So we'll continue our discussion on this causality. This is actually for IIR system. We will look at FIR system later on Thursday. Okay, so any question? So last call for any questions. Okay, I think no question. So, okay, so that's all for today. So see you guys again this Thursday, okay, at 10 a.m. Okay, bye everybody. Assalamualaikum warahmatullahi wabarakatuh and good afternoon.
Thank you, Doktor.
Terima kasih, Doktor.
Sama-sama.
Thank you, Doktor.
Thank you, Doktor.